What were we talking about last time? Circular motion, okay? Uniform circular motion where the speed doesn't change but direction is constantly changing. And we found out some quantities, right? There was an equation for something. What comes back to your mind? Circular motion, okay? And what else?
Acceleration equals v squared
Okay.
over r.
So that acceleration, which we call centripetal, or some people call radial, v squared over r. And what was the direction of this acceleration? Here I have my, yes, who said that? Yeah, right? So the acceleration is always towards the center of this motion. That's why it's called centripetal or radius. It's always along the radius, right? V squared over r. What else? What else did we learn? What else did we discuss? Yes. No? Okay. What else did we talk about?
The tension force is heavy, is like stronger at the bottom.
Okay, there was this story when we are doing the circular motion in the vertical, that the tension there at the bottom is stronger to overcome the weight. At the top, the weight actually helps us. This is a good point. Anything else? Any other equation? Any other concept?
Period versus frequency.
Yes. We had this equation that period is 1 over the frequency. And what is period? What is frequency?
Time to go to do one cycle.
To complete one cycle. That's the period,
And
right?
frequency is the amount of revolutions per second.
Very good. There was also an equation for the v, for the speed in this uniform when the speed doesn't change. How did we find that?
It's 2 pi r over t.
Very good. That was the circumference and the time to complete the circumference. Yeah. What is the direction of the v in this circular motion?
Tangential.
Always tangential. So if my rope breaks, I move away in this tangential. Good. Okay. So we talked about some motions, and then we started now talking about the car. The car that is trying to curve. So here we have the car trying to curve. And then we said, well, it will only be able to curve if there is friction. Which kind of friction?
Static.
Static friction. And pointing where? Towards the center. So this is going to be the force, which is the force of friction, which is static friction, that will allow our motion. So this will be my net force. This will be equal to ma. Okay?
And acceleration.
So this
It's
if
all
if I sum all of the
right.
forces, which will be this one only, equals to ma.
MA.
And that a is the centripetal acceleration. And then I said, okay, but if this car, so this is the car that is really turning and being able to make that curve. But if this car is not able to do the curve, so here's the curve, so the car slides, skids out of the curve.
Why is it static friction?
We'll come back to that. It is static, everybody got that, but I'll come back to this explanation. But here, if I'm not able to turn, if the car is skidding, there is also friction, but what kind of friction? This, in this case, will be kinetic, and this will. So my car is moving in this direction, and this will be kinetic. Okay, so now comes always this question here. For this, when we do make the curve, how come we are talking about static friction if we are actually moving? So how can we explain the fact that this friction is static? So different things that we are going to discuss. But first point, if you look at the tires, in this case here, where we are skidding, what happens to the tires? They get locked. They're not rolling anymore. They get locked and they go just like our box. So it goes on skidding, just like the box here. And that's the frictions against this motion, against this skidding motion, and that's kinetic friction. Here, I don't have that. The tires keep rolling all the time. So there is no motion of each point of the tire with respect to the surface. See, each point touches and goes out, touches and goes out. So each point of the tire, they do not skid. Okay? So this is one thing. The other thing that how we were trying to convince ourselves of this static comes from relative motion. So remember the story of the train. Here we had the train accelerating this direction, and inside the train we put a box. What guarantees that this box will move together with the train? Friction. And this is static friction. Static, why? Well, you're saying the train is moving. Yeah, but the box is not moving with respect to the train. So it's static with respect to the train. Do you see that?
Because the acceleration forward would make the box move back.
Yeah.
Because of the friction, it's moving forward.
Yeah.
Well, it's saying stuff.
What would actually happen is the box would just want to stay where it is. Now, there is no engine at the box. So the box just wants to stay. What it actually, if you look from the train station, what you would see is the box there and the train moving. Okay? But what guarantees that this box goes together with the train? The friction. Okay, in the same direction.
So it's not moving in relation to the train? That's why it's static?
That's why it's static. The box is not moving with respect to the floor of the train. The train is moving, the box is moving, but the relative motion of the box with respect to the train is not. So coming back to our car here, I'll come back to it, just finish. So coming back to us here, I'm sitting on that car, okay? How come I turn together with that car? Friction in this direction. My motion with respect to the car, if there was no friction, with respect to the car, would look like I was going against the window of the car here. What keeps me moving together with the car? The friction. Do you see that? When you're turning, well, if you're the passenger, okay, so someone is turning for you and you were distracted, if it's a sudden turn, you can hit the door or the window of the car. What prevents you? What allows you to curve together? Friction. So if you think about this relative motion with respect to the car, you see that the friction is against.
Well, how would friction help the passengers?
If there was no friction, okay, if suppose you're sitting on ice, the door is open, no window,
Right,
no seatbelt, you would fall out.
Right, so how would friction keep you there?
Because there is friction between my body and the seat.
Mm.
So if you don't move too fast, that's the problem. If you move too fast,
And then you
trouble.
exceed S max. S max.
Then you would be exceeding our friction force. Okay, but let me just finish. So this is the motion of my body with respect to the car. Someone outside the car just see, oh, she wants to stay where she was. The car was moving away. Yeah.
I understand how the box is static, like relative to the train. I don't understand how the train here is static, like relative to what?
So I'm talking about the passenger.
Oh,
The
no.
passenger with respect to the car is static
Okay,
because
fine.
there is this friction. Okay, so that's the same thing, and then you go on extrapolating this idea and all the way to the tires of the car, the tires that do not skid, the tires that just keep rolling. All right. No, there was a question.
So I'm just like imagining a person on the subway car, and who's like standing up, not holding on to anything, and then when a train initially starts to move, you like will like fall back a little bit.
You do because you just wanted to stay where you were. Although, if this train does not move too fast, now if it's a good conductor there, you can. I many times I go on the train without holding. Yeah? So because friction holds you. But if this speed is too big, then yeah, then the friction doesn't hold.
But when it starts pulling out of the station, like, I know, like, I fall back not when the train is moving at a normal speed, but when it's, like, pulling out of the
Starting.
station.
Yeah,
Yeah.
starting because that's when the trains accelerate before it reaches the continuous uniform velocity. That's the big problem, is the acceleration. Alright, so that's the story. Now what we want to know is, are we be able to make this turn or not? Will the friction, the static friction, hold us there or not? And that's the problem here. So we have a car, 1,000 kilograms, okay, on a flat road, so there are no angles, no inclines, flat road. The radius is 50 meters. And the speed, we want to see, is the speed too large or not? The speed is 14 meters per second. So we want to know if he will be able to turn or not with this big speed. Well, if it's big or large or small, it will depend on the problem. There are two cases there. The first case is the same curve, nothing changed, same curve, same car. But one day he enters that curve and it's not raining, the pavement is very dry, so the coefficient of static friction is 0.60. The other day he comes to the same curve, same speed, same car, but it's raining. Okay, so the pavement is wet and the coefficient of static friction is not as big anymore. It's 0.25. So we want to know if he will be able to turn or not. What would you do? What would you compute here?
First step of force is equal to mass times acceleration.
Okay.
First steps.
What we are going to do is, we want to know if the sum of all the forces, the sum of all the forces will be equal to ma. But we want to know if the sum of all these forces here
Equals 0.
will allow us to do this turn. Yeah? What is it? What is
Just
it?
knowing if it's equal to 0 help because you want it to be static technically.
Ah, careful. We are turning. We want to turn. If we manage to turn, there will be an acceleration. It's friction. The friction is static, but there is a centripetal acceleration.
So
Okay, so we don't want to put this equal to 0. Good point.
So we're looking for the friction force, and we want to make sure that it's more than whatever the other force is.
Very good. That's what we want to see. We want to know if this friction force, which is static, remember that static friction force can go to 0 all the way to a maximum value. So we want to know if this maximum value is larger or equal to the ma. If it is larger or equal to the ma, what is the a here? The a is determined by the speed. Okay? So if it's larger or equal to this ma, then I'm safe. Then I have enough friction to stay on this motion. Did everybody get this or not? Yeah. How can I, on the train, with the box on the train, how could I guarantee that the box would move together with the train? If that friction, let's go back to the train. And here we have the box. The train is moving with a certain acceleration. What guarantees that this box goes together with the train? If the friction of this box with respect to the train, the static friction, is equal to ma. Okay? If it's not, if this friction is too small, what will happen? The box will end up hitting the back of the train. Okay, so the friction has to be equal to this ma.
Or more than? Or no, it has to be.
Now, remember that this static friction varies. No? It goes from 0 to its maximum value. If the maximum value is larger, I'm safe. I won't even need to go all the way to the maximum value. I just go on adapting myself to my needs. Right? So if this maximum is larger, I'm totally safe. Or equal. Equal will be the limit. A little bit more, and then I'll scale. So let's start computing what is this friction. What is this maximum value for the static friction? So let's compute here and here. I'm going to compute the maximum. I may not need to go all the way to the maximum, but I want to see if the maximum is larger than what I need for this speed. Okay, so what is the expression for friction force?
Mu s times Fn.
Very good. So mu static Fn. So I'm just going to put it. Then what is Fn? Here I have my car on this horizontal surface. So yes, very good. In this case here, horizontal, no incline. So mg is pointing down, Fn is pointing up. My Fn in this case is just mg. So there I come back here, ms, mg, also here.
Wait, are we talking about the curve or the this one or the?
This is the car. It's going to curve, but all on the horizontal. So I'm just putting here the forces in the y direction on this car. So it just has weight and Fn in the y direction. Okay, I'm not putting the x direction yet. Okay, so let's compute these two numbers. Can you get it for me?
Yeah. It's
9800.
5,880 for the top one.
Okay, so this is big, of course, because the coefficient was 0.6, and this one
2,450.
2,480.
2,450.
Okay, and this is small, so let's watch this one. Huh?
Wait, so this is only the y direction. That's why there's no acceleration.
These two forces are in the y direction. The Fn and the mg is in the y direction.
But then, like, how do you get the Fn equal to mg?
Because of this, if I sum all of these forces in the y direction, this is my frame. What I have is Fn minus mg. My car is not jumping up or down, so it's not moving in the y direction. This is here.
Okay.
So we got the two maximum friction forces that this pavement will give us. Can I erase it? Yes.
Wait, if we're doing sum of y, like sum of forces in y is Fn minus mg, then wouldn't it be Fn? You can change the Fn equals mg, and then it would just be 9.8 times 1,000.
Right.
But the answer that we got for A was
Because here I'm not
times mu
O
s.
times mu.
Yeah, this is a friction force. Okay, so I have the values for friction force in case A, friction force in case B. And what we want to compare, this is with MA. What is MA? Is what is this A that I'm writing about? So let me put it.
The acceleration from the center.
So this is my car. We are trying to curve. If I manage to curve, if I manage to complete this curve, I have this acceleration, which is the centripetal acceleration. So this MA that I'm talking about is centripetal acceleration. So I'm comparing this maximum friction force with MA. Alright, so what is this MA? As I heard people here saying, is the mass of the car, 1,000, and the centripetal acceleration, which is v squared over r. Let's put all the numbers there. 1,000, v squared is 14 squared, r is 50. Which number do we get here? 3,920. Okay, so this what we get when he enters with 14 meters per second in this curve that has 50 meters for the radius. With this car, there is 1,000 kilograms. If I compare this with the maximum friction force, in which case is the friction force good enough?
A.
Does everybody see that? A is much bigger than this. So in this case here, he will be able to curve. He just needs, from this maximum amount, he just needs this 3,920 and he curves. This one, this friction that is given to him is too little. So he cannot curve. He's going to just skid over.
Do you mind drawing out the force vectors, please, for in all directions? Because acceleration is going to the right, force of friction is going to the right. What's the force taking it to the left?
So if we curve, so this is only if we do make the curve. So this is the net. The centripetal acceleration comes from the net, sum of all the force. What is the only force that I have here in the x direction? Only the friction. And this is static. That's it. I can also make the Fn and the mg perpendicular in the y direction, but in the x, that's it. There is nothing else.
So what's to stop us from flying to the right? What's the force counter?
This is the one that allows me to turn. There is nothing against it. This is already the cause, the consequence of the motion. Just like when I was with my ball, it was just tension force.
Oh, right, the force.
So this friction now is the role, plays the role of my tension force before.
We're trying to move to the right.
Yes.
Okay, I get it.
And if you don't make the curve, then acceleration would continue on.
If I
Straight.
don't, let's make the drawing. If I do not, okay? So do not make the curve. If I do not make the curve, there is no centripetal. So I cannot draw this centripetal here because it doesn't exist. In my car, it's just going.
What forces?
So what would I have here?
Acceleration forward.
I would have some acceleration forward because my velocity is changing here.
And friction
And I would
straight
have
up.
friction kinetic against. So it's a completely different problem. And now we erase because that's not the one we are in. Let's see, there are many questions. I'll go one by one.
But in this problem, even though when the ground is wet and there's less friction, it's not like kind of formulated correctly. There's not enough newtons to overcome the force of not the force of friction. The other
We don't
force.
have enough force to allow us to turn,
Right.
right?
But you still turn a little bit, don't you? Because there still is friction. So you're not going to go straight. It's just different degrees of turning, isn't it?
You would go, keep going straight. If it's really icy, as it happens, you may have had this before, dry. You just keep going.
Isn't if there's any friction, it would get you a little bit off course?
There is, if you, it's like when I was turning my ball, like the guy yesterday that we saw the movie, right? Once he let it go, it goes tangential. It's true, there is some little friction there still helping us, so maybe you curve a little bit and you go in a funny trajectory, yeah? But you'll get out of that curve that we are trying to do. Yeah, and there you go.
I have two questions. One is, so in this problem, we don't have any motion in the x direction? I mean, like, it's not, like, we don't.
We are not going to go like this. Yes, we are not. We just keep turning.
Okay.
Because there is a velocity here.
And then also,
So it's the same drawing that we drew today when we started the class.
yeah. Also, why wouldn't the friction be opposite acceleration?
The friction, the force is what causes this acceleration.
Yeah.
So sum of all the forces is equal to ma. This is the only force. This is equal to ma.
No, I understand that, but I'm saying, like, why wouldn't friction be going that way?
Because then the acceleration would go that way. What is the equation? Sum of all the forces gives me Ma.
Yeah.
Remember the problem of the tension. I had the rope, I had an object there. I was turning. Where was the direction of my tension force? On that object, if you had to draw. So let's make this drawing. This is my circle, my ball. Here is my rope, and here I am. Okay. Where is the force on that ball that I am exerting? The tension force. Which direction would you put for the tension force?
Down.
Towards me, right?
Yeah.
And what is the direction of the acceleration?
Also towards you.
So you see that it's the same thing as there.
I see.
This is what allows the motion to persist.
Okay.
Okay?
So the friction goes towards the center also?
Yeah, because the friction now plays the same role as the tension here.
Okay.
It's the force that causes this motion.
Okay.
Laura, there was a question or not anymore?
Yeah. In these questions, so far we haven't used anything with the sum of the forces in the x.
This is the
Does
one.
it ever come into play?
This is the one. In the x, I summed all of the forces and there was just friction. So this is the sum of all the forces in the x equals to Ma.
Oh, so the force, because we wrote it out in the y,
In the y, there are forces in the x
right?
and there were forces in the y. Okay? This is the x and the y is coming out of the plane. So in the y direction, there was just the weight of the object and Fn. That one I drew so I could get Fn. But in the x, the only force that I have is the friction. So the sum of all these forces, which is just the friction, is equal to Ma.
Why isn't the y this way, like in the same direction of the curve going back?
This doesn't move. I can move this, okay?
Oh, because it's like this street.
Yeah,
Looking
it's
at,
this
like, the
street.
street
Yeah, so
along
the
the-
street is here. Okay, so
Oh.
this is this. All right, so we got that A, we are able to turn, and B, we are not. Everybody follow? Good? Now I have a question for you. When you go out driving and you're getting out of the highway, did you ever notice that to curve there is actually a little incline? Sometimes you even turn a little bit. Have you ever noticed that?
Yeah.
Yeah. Good. Yes.
It's like, yeah.
There is a little incline, and my question is why? What is the purpose of putting an incline?
You're going 60 to 80 miles an hour on the highway. You're trying to get off back onto local roads. You go from incline, you're going to slow down.
Yeah, they usually put a different speed limit there because we enter the curve slower, less than 60 miles, and good. We are going to see why we are slowing down, but the reason is this, right? Is to allow skidding. But why do they put these inclines a little bit?
The gravity force pulling you down can contribute to the friction force, so that you can kind of take a steeper, not steeper, but like take a curve that's more sharp without flying off.
That's the idea. That's very good, and let's make a drawing to see that. But the purpose of that angle, that incline, is that I can turn, I can complete that curve even if it was an icy road, even if I had no friction. That's what is in the mind of the engineers when they put that angle. So let me try to make a drawing here, and let's see if you get it. Some engineers are very bad and they don't do it this correctly, and then it's a disaster. But if they do it correctly, we'll see. Look at this. This is the incline of a certain angle, and this is my car. I'm going to show to you another drawing here that is probably better than this. Because not everybody gets this immediately. I cannot see this. Can maybe let's put it down the. Can you just turn off the light? I don't know if it will help much. Can you see what is going on here? This is the incline, okay, and the car is here. What is the car doing? It's turning around. So this whole curve keeps the car is going along this curve, but always in this incline, in this ramp. Yes.
Oh no, I was just gonna say it's kind of like a racetrack. Where
Yes.
it's
Yeah.
like
That's the
all,
best.
I was thinking we're like a skateboard.
Yeah,
Yes.
like ramps.
If you played with those toys, have you played with
Hot
that?
Wheels.
Yeah. Hot Wheels.
Like the ones that they
Then
do,
you see it
it's all
immediately.
like this.
Yeah, I played a lot because my brothers had it. I loved it. But if you have never seen, you can check on YouTube. How is it called? Race toy.
Hot Wheels.
Yeah. Okay. So check and you will see. And what is the purpose there? Be able to turn. And if you enter with those little cars with a huge speed, you see they fly out. No, so you have to enter a little slower when you get into this curve. So, but everybody sees what kind of curve you're studying. So there is this incline. The center is here, and I keep going around. Okay? So now we can turn on the light. Let me come back to this. Drawing from the book. Alright, so remember, my car is going around and around in this incline. So if I had to draw, the centripetal acceleration, in which direction would I draw? The center of this motion is here, okay? And I keep going around. Where is the direction of the centripetal acceleration? To the right, right towards the center. So let me put this further. This is the direction of the centripetal acceleration. Yes.
Why is it not diagonally down to the right?
Diagonal down to the like this. You wanted to put?
Why not?
Because you could, if there was a problem from chapter 4, which is my car is sliding down. But my car is not sliding down. It stays always this much far from this point, and it just keeps going around this curve like this.
Okay.
You see it really?
So we don't have any horizontal motion.
No.
So in theory, it could be from down there, but since we don't have any horizontal motion, it has to be the.
There is no motion
no
along the
vertical
ramp.
motion.
So this is my car, okay, and never slides down. It just keeps going around like that. Okay. All right. So this is very important to get to the direction of this acceleration. Now let's draw the force. What I want to do in this case is I want to be able to turn without friction. And so, as Lior was telling us, we can do that if we take into account this contact with this surface. Okay, so I'm going to put the forces that we know is always there. Mg is always there. And we have, touching the surface, Fn, perpendicular to that surface. If you look at these two forces, is there any component of these forces that you could imagine being in the direction of the acceleration? Any component of these forces that could allow this acceleration to exist? Fn. But let's decompose and you will see. Remember in chapter 4, what we discussed was, how am I going to choose the reference frame? We decided to choose the frame to make our life easier. Choose the frame always so that one of the axes was along the acceleration. In chapter 4, the object was sliding down. So this was the axis of the motion. Here, this is the acceleration. So which kind of frame would you choose?
You would go along the acceleration.
So the best frame is this one. You can always choose any frame, this is arbitrary. But this is the best one, so I don't need to decompose the acceleration. So you see that this choice is different from chapter 4, so don't mess up these kind of problems. Chapter 4 is I'm sliding down, so my acceleration is down. So that's why I picked that tilted frame. Here, I'm rotating. I don't slide down. I'm always at this far from this point. Always at the same distance from this point. So my acceleration is that one, the centric.
So you also don't have to decompose gravity.
Very good. So in
There's
this problem here, I don't touch mg. Mg is already in the y direction. So let me put this is my y direction, and this is the x. Now the fn, the fn, I can pick a component of fn, which is in the x direction, which will allow me to curve.
mg sin
Mg
sin theta.
It will be fn in the x direction. Now let's see what is going to be the value of that. Yeah,
fn cosine theta.
you may be right. You may be sine. Let's see. Let's double check the angles. Okay. Before I draw the angles here, let me see if you've seen this before. If you have this colors too. Okay, so these lines are parallel. My drawing is not so good, but these lines are parallel. Okay, if I tell you that this angle is theta, what is this angle?
Theta.
Okay, everybody knows that. Okay. If I say that this is theta, what is this one?
Theta.
And this one?
Theta.
So now let's try to do the same thing here. Okay. I'm saying that this one is theta. How about this?
Theta.
And how about this?
Theta.
Now, this is the surface, this is Fn. So I know that this is 90 degrees. Fn is always perpendicular. What is this one?
90 minus theta.
Okay. X and y are perpendicular. What is this one?
Theta.
So you see that you know all these angles. To decompose Fn, the best one is to pick this one.
Pick which one?
This one, huh? So I can decompose here. I can make a triangle. Let me make this triangle.
You want to use that 90 minus theta there?
You can, if you prefer.
You want to use
I'm
which
going
one?
to use this
that
one.
one. Yeah.
This is my Fn. The triangle that I'm selecting is, remember I have to make the triangle parallel to the axis, right? So this is parallel to the x. So this is the triangle I'm playing with. So this is the Fn in the y. This is the Fn y component. And this is the Fn x component, which I can also put here.
Why do you do that one instead of I guess
It's up to you.
Okay.
It's just because I don't want to keep carrying this 90.
Yeah, but
I
can we just assume you have 90 minus theta, a 90 degree, and then where the regular Fn arrow tip is, just put theta there?
Here?
Where the tip of that arrow
Here.
is. On the other side. If you draw the y.
Yeah. This is 90 minus theta, and this is what you want to do. You want to come?
The way I immediately saw it is this is 90 minus theta. We have this angle right here is 90, so this is theta.
Yes.
And then we can see right here that that's the
Yeah.
x component.
Yeah, you can do that. There are many different angles that you can choose. Now, there are too many angles there.
Why does the reference frame start from the middle of the car in the picture?
Because when we are thinking about these objects, we usually think about them as a single point. So we think about the exact center of the car. That's why the best way to make this drawing is to avoid putting any forms. You just put this point. So that's the center.
But wouldn't you want it to be the one that's against the ground?
Say it again.
Why wouldn't you want the point to be the one against the ground? That's just like floating in the air.
But the the object is touching the ground. There is a whole shape for this object. You're right, but I'm thinking about a center. If I think about a single dot, that's what Galileo did. He didn't think about the arms and legs of the person. Just substitute the object with a single point. So all the forces that I draw are on this point.
So, but that one, if you keep going with the X, the transversal cuts across at a different place, so you don't get the same
Angle.
theta. Yeah.
You should. You get, because remove that car, put a dot. Okay, this whole problem is done for a dot.
Okay.
If you go on trying to take into account all of the different parts of this car, yeah, it gets incredibly complicated. But we'll think about a dot. Okay, so now let me, did you see? If you want, you can also use this theta here, so Dea is going to use. I'm going to keep using this one, okay? It's up to you which one, but let me draw. I'm playing with this triangle here. Okay, where this is my theta. So help me. If I look at that triangle there, what is F and Y? Is it touching my angle? Is it adjacent to my angle? Is it opposite to my angle? Okay, so this side here is Fn cosine of theta. How about this one? Is it opposite or adjacent? Is it cosine or is it sine? Yeah? Alright, that's all we needed. Now what we are going to do is, remember what was the origin of this problem? We are trying to curve without friction. We are trying to use only the normal force to still be able to turn. It's an icy road, so the friction is tiny, tiny. And what we want to find out is, we are these engineers, we want to find out, okay, I have to build this road, I have to build this curve. What is the angle that I'm going to use? And what is it that I'm going to write in the sign? Which speed limit? I'll tell these people. Okay? Okay, so I'm going to write all the forces in the y direction, all the forces in the x direction. So let's start with the y. What do we have in the y direction? And the frame is up is positive and to the right is positive. Fn cosine of theta is our y, right? So Fn cosine of theta is plus minus mg. Do we have any motion in this direction?
No. Equals 0.
Equals. So from here, we find that Fn is
Equals mg.
mg divided by cosine. Okay, so let me keep this in this box so I can use it later. Let's go to the x direction. Sum of all the forces in the x direction. What do I have in the x direction?
Fn sine theta.
Only that. That's the only force that I have in my drawing. So it's Fn sine theta and nothing else.
Equals
That's
mn.
acceleration.
Ah,
Force of friction.
acceleration goes to the right side. In the left side, I just sum all the forces.
What about force of friction?
It doesn't exist here. This problem, I'm trying to do this curve without friction.
Okay. Assuming I assume negligible.
I'm assuming that the friction is negligible. Okay. And so did you get sum of all the forces? After I sum all the forces, the net force gives me ma. Okay? So I sum all the forces that I have in the x direction. Now I'm going to put the ma, but on the other side. Okay? So here I come, it's going to be m, a, and a is the centripetal. What is the expression for the centripetal acceleration?
V squared over r.
V squared over. So what I'm trying to find an equation for the angle. So I want to connect angle with speed. So I build this road and I tell people what is the speed limit.
So it's Fn equals mv squared over sine theta times r.
Yeah, but can't I get rid of this fn? I don't know what is fn.
Right, so don't we want to isolate it? Or can we,
How about if I put this one here?
Yeah.
Let me see her question, I'll come to you.
Oh no, that's what I was gonna say.
Yeah. Okay, so I already isolated n from the y. So I'm going to put it here, and I'll have an equation that only involves now the angle and the v. Laura?
Can you always replace MA with MV squared over R in some of x?
If I have a uniform circular motion, then it's going to be this centrifugal acceleration. Okay, so now I put this Fn here, mg, put the sine of theta, make it more explicit. Mg, sine of theta, cosine of theta. Okay, so this is my left side, equals to mv squared over r. Anything that I could cancel?
tangent.
Okay, you were faster than me. That's why you wanted to say also.
Yeah.
And Liora.
Like mass and tan theta.
Mass. I was one step before and you were already rushing. Yeah, I was going to say, well, let me get rid of this mass. And these fast people, they're correct. Sine divided by cosine is sine. Right? So then we have, put it, tangent of theta. There is a g, so let me not forget it, equals 2v squared over r. So I'm going to write the equation just for the tangent on one side. I have tangent of theta equals to v squared over r. So this is a very nice equation, and that's what the engineers have in mind when they build the road. When they put the v there on the sign, that's what is in their mind. So you are able to curve even if it's a little slippery.
But I thought that the question you had to answer what's the theta and also what's the speed.
We were after this equation. Now, if I tell you the theta, you know what is the speed you should enter. Or if I give you the speed, you know which
So one
theta.
of them determines the other. It's not like pick both.
Yeah. Here, let's see what the question was. Determine a formula for the angle. It's not very well written. It was find this formula that connects the angle with the v.
How did they find the radius in this sort of situation? It's not like we have a complete circle.
You don't have the complete circle, but you have the arc. So if you know that if you would close, you know what would be the radius. Okay? So you have the arc. Good. Common question. Sometimes these kind of problems show up in the exam. If you just write this equation because it's in your mind, I don't like it, okay? Please show everything, how you arrived here. Don't just, I remember that by heart. No. Show that the drawings, the forces, some in X, some in Y. Yeah.
So you're saying when you have a question where you're trying to figure out the angle, you want us to show all of this, that we got this equation, like you can't just use the equation?
But I'll put a note there. Okay, so you remember. Keep it in your mind.
To answer 5-7, would you have to isolate the R on one side and everything else on the other side? The radius and the
You can put it you can write this equation in any way you want. You can keep it like that. You can put the R here. This is the equation that connects the angle with the V. That's what we wanted.
The only reason why is because it's asking for us for an equation for radius R. So wouldn't it want an equation with radius
So
R?
for a car that has this V
Right?
with this radius, so V and radius are there, determine a formula, an equation for the angle. That's what we did. For angle, V, and R. So everything is in that equation.
And then, well, if you look at the one that was used for that until we divided the gravity, the G10 tangent,
This one,
no, to the left.
this one,
That wouldn't that answer it more correctly because it has the velocity and the radius isolated?
it's
It doesn't matter.
they are the same exact equation. It doesn't
You want to isolate the angle?
Okay, so that's the equation, yeah? These two next slides I'll just pass quickly. This first slide here, it's going to be important only for chapter 8. What this slide is telling us, well, if I'm on this circular motion, we already agreed, we all understood, we always have the centrifugal acceleration. No, so we always have the centrifugal acceleration. We are fine with that. But suppose that I'm on this circular motion, but my speed is increasing. My tangential velocity is increasing or decreasing. So that means I would also have a tangential acceleration. Okay, and this will show up in chapter 8. I could have a combination of two accelerations. But here is just for you to know. The next slide is the one just an application of this circular motion, which is the centrifuge. Have you ever played with a centrifuge? What for? Used it.
Yeah.
Yes.
For what?
Labs.
Separating.
Okay, you
By
wanted
weight.
to, yeah. Oh, so there was some substance mixed there that you want to
Putting
separate.
bacteria on the bottom, or cells on the
Nice,
bottom.
very nice.
Separating out blood cells.
Putting supernatant liquid.
What is that? A super liquid?
Supernatant.
liquid.
What
It
is
means
that?
the
Supernatant,
liquid that
yeah.
doesn't have the stuff that you're.
Meaning it's
Ah.
the lightest
Separate
possible. It's the lightest possible of the entire mixed solution. So you sometimes want that, or you usually actually want to clear that so you can have your material at the bottom.
Remove, separate those parts.
Right.
All right. So let's think about bacteria or any of the things that you wanted to remove. This is our A. Okay. If I had a rope, this doesn't exist. But suppose I was in the middle of that centrifuge with my rope, and I was holding that A. The A would always be the same distance, not the distance of the size of my rope. So it would keep always there. But my A is free there in this solution, in this liquid. So, and this liquid doesn't have much tension. If I keep rotating, what happens? The A would like to stay where it is. And what happens? The whole tube moves. So the A just tries to stay where it is, but the whole tube moves, and more you will see that this A, this bacteria, stays closer, gets closer and closer to the edge of the tube. Just like in my car, I touch the window of the car. No? So that's the same thing.
So is your R getting smaller in this situation?
The R,
When things go towards the bottom of the tube?
but they go to the bottom, so this is getting bigger, right? The R. If you think of the radius for the particle A, the radius was little like this, and then it's getting larger. Getting closer and closer to the edge of the tube.
The tubes aren't in there together, right? It's just like you're talking about tube A or maybe tube B.
Ah, okay. It is the first picture that I took. These drawings, huh? So forget about this. This is the first picture that I took. Some seconds later, I took this picture. So the same tube
Oh, okay.
at different time.
So it's moving outward or inward?
With respect to the tube, that bacteria will get closer and closer to the edge of the tube.
Like 4 feet, like farther away
Further away from you. Okay, so this was just some qualitative thing. Now let's go to a real new topic. They have to keep changing that. Which is the gravitational force. We already talked about it. When we started talking about this circular motion, we said, what keeps moon turning around Earth? What keeps Earth turning around the sun? What keeps the sun turning around the galaxies? What keeps the galaxies turning around each other? It's a crazy thing. If you start thinking about the universe out there, you disappear because it becomes smaller and smaller. So, the force involved in all of these celestial bodies, motion, and clustering is the gravitational force. And what is the idea behind? Well, everybody puts Newton as if he was the great discoverer. Of course, it's not only one person, it's one of the main names. And that story of the apple, you must have heard, right? The apple fell on his head and he got the great idea. That's a legend, right? But No, you don't get to illuminate it like that study. It's many years of studies and so on. But what is the idea? Let's pick Newton's apple. If I drop, it falls. If I go on top of a tree and drop, it falls. If I go on top of the mountain and drop, it falls. So always falling. What is the cause of that? The conclusion is, well, it must be Earth that keeps attracting everything towards it. Okay? So what brings this object back is Earth. Okay, so it depends on the mass of Earth. But if I keep going further and further, I went to the top of the mountain, and then I took a plane, and then I took a rocker, and if I go further and further, eventually I'm not going to fall anymore. I'll get lost in space. Gravity won't have enough force to bring me back anymore. Okay, so the conclusion of this story, summarizing the story, is that this gravitational force depends on these two objects involved. It's Earth and the apple, it's Earth and any of us. So it depends on the mass of Earth and depends on the object we are studying, but also the distance between them. If I go far, far away, this force will fade away. Okay, so this is, and it depends on the r squared, 1 over r squared. So as the further I go, the weaker this force will become very fast. And there is one more thing that I should put in the equation to keep this equal sign, which is this constant, big G. We talked a lot about little g, but now I have this big G. So let me show to you the next slide. So what we have is here, there is Earth. Here there is my apple. And what we are saying is that the apple attracts Earth, Earth attracts the apple, so it's action and reaction. This force is gravitational force. It depends on the distance between the center of Earth and the center of the apple. Okay, so this is the R that is showing up there. So that means if I keep putting this apple further and further and further, this force will get weaker and weaker and weaker. What does it mean in terms of weight? And
the farther away you are from the center of gravity, less prone to fall.
Yeah.
So if
You're
you
going
weigh
to weight
yourself on a
less
plane,
and less.
you weigh less.
Say it?
So if you weighed yourself on a plane, like if you're on an airplane, you would weigh less.
You will weight less and less, to the point that if you go into a rocket, you see the astronauts like flying there. There is no gravity anymore, or very little. Now, so if I go further and further, I weigh less and less. What we've been using so far, we just used the equation for the weight was, for the apple, for example, was the mass of the apple, g, little g. This is the same thing as that. So let me put an equal sign here. This is the same thing as that. If you compare these two equations, what do you conclude about little g? What is little g? Do you agree that little g, if this equation, the weight, is equal to that, the cause of the weight is Earth, little g is this. So little g is determined by this constant, this gravitational constant, this big G, which is a universal constant. It's always the same value, no matter where we are, at least in this part of the universe that we know. So this constant is always the same, this big G never changes, but the little g will depend, the little g on Earth depends on the mass of Earth, and it depends on how far we are from the center of Earth. Any conclusion out of that? Yeah.
Isn't Earth an oblate spheroid though?
We
So then
treat it as a sphere. Yeah.
So then, how do we have a constant if it's going to be different depending on where you're?
Very good. We don't. The little g, we kept saying, little g is 9.8, 9.8. Yeah. If I'm very close to the surface, then what I put here is just the radius of Earth from the center to the surface. But if I go up, 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 this g will get smaller and smaller. That's the whole point. The g is not a constant. It depends on how close we are to the surface. Yeah? You had a question? Yeah, it's you. No? So, we kept saying 9.8 because the radius here from the center of Earth to the surface is like 6,000 something. If you add 1 meter or 2 meters, it makes no difference. You will keep getting that 9.8. But if you add to that 1,000 meters, this g will get very small. And if you go very far from Earth, that g just becomes 0. So it's not a constant. All right. Question for you. You know that Earth is much bigger than the moon, right? If you go to the surface of the moon, what do you expect for the g of the moon? Bigger or smaller than the g on Earth? Smaller. And if you go to Jupiter, Jupiter is much bigger than Earth. It's a huge g. You cannot raise your legs. You would die also because of lack of oxygen.
So
Okay.
we would die from pressure also, just because we wouldn't be able to.
Probably we wouldn't be able to stand. You know, the cells, or the way that we are made for this planet. It's very interesting.
So there's this movie coming out about this boy who lived on Mars, and so he's trying to go back to Earth, but he has like a lot of body problems because he was born in like 0 gravity. Is that scientifically a thing?
Not 0 gravity.
He was born in Mars gravity.
No, I think he was born not in Mars, like on the spaceship. to
He's
Mars.
okay.
And
This
then
must
he
be fun.
lived
This
in
is
Mars.
a movie, a science fiction movie.
Yeah.
Yeah.
That would be nice to watch, because in these science fiction movies, many things are real and some things are completely crazy. Like there's explosions happening out in space is crazy because there is no way for the sound to propagate. So you should never hear the explosions out in space. You could see the explosion. And so in this case, he must be a creature that was born and well adapted to this lack of G. Yeah.
So it makes sense then that he would have like a lot of physical problems.
He's a creature adapted to this other scenario. And also the same thing for the astronauts who go out. A lot of preparation and not everybody is fit for that. And you cannot stay there forever. Yeah, there are many problems. You lack the muscles. You have to do exercise.
So random question, did you see the movie Interstellar?
No.
No?
Why? I
It's
should-
all based on physics, and like I thought it was fake, but then I found out it was all based on real stuff.
And so they had like scientists behind to make the
Yeah,
movie
like
real.
physicists.
Mostly.
What?
It was like mostly.
Well,
Mostly, like-
physicists wrote it, and it's like all based on like real theories. And, I
Yeah.
don't know, it was
The-
like crazy.
People in the cinema, in the theater, they usually get scientists to check. Does it make sense or not?
Yeah,
that's
I don't
nice.
know.
Okay, so conclusion out of this equation. Oh, this equation here. Earth attracts everything, but not just Earth. I am attracting Earth. I'm attracting the table. The table is attracting me. How come I don't collapse into the table? Friction. Otherwise, it would be a mess. We would all be collapsed. And
Because of friction, isn't it because the like gravitational force is like very little?
the force between me and the table is tiny. You're right.
Yeah, that's what. It's not because of
But if
friction.
there was no friction at all, if there was just this tiny force, yeah, we would get close together.
If you and the table were floating in space,
Yes.
you would get pulled together.
Yes. Exactly.
Then why is it again in all the movies when an astronaut floats away, they float away?
But if
So
the
that they get
astronaut,
pulled back to the ship or whatever.
is it already far, already outside the gravity of Earth, then it's floating out. But if it's still connected, if it still feels the gravity of Earth, it would come back. That's what happens to the satellites. The only way where you would not fall is if you have a speed. Okay, what she asked is very important. She's saying, okay, so I put someone out in space, far from Earth, but still in the vicinity. And I want to know, is this guy going to fall back on Earth, or is he going to fly away? Depends. If I put him there without any speed, still in the vicinity of Earth, yeah, he will fall back. The satellite also will fall back. But if I give a speed, a tangential speed, if it's the right speed for that height, the guy will be forever in orbit. But if I give a very big speed that is more than the necessary for that height, he will fly away. So that's the same problem with the satellites, and we'll talk about it.
So that's how they have those things orbiting Earth?
Yeah,
Because they put them at the, how do they figure out the right speed?
we will figure out today. Tomorrow, no, Monday probably. But we will figure out what is exactly the correct height for a correct speed so that it stays in orbit forever. Okay? Okay, so this problem is just compute what is the force between these two people. So you just put the mass of these two people when they are 0.5 away. And you put the value of the g and you get this tiny number.
Wait, why would you put a person who's so massive? Would you
If-
also
if
put
I-
a massive Earth?
No, you put the two objects involved. If I'm studying just these two people, I put these two people. If I study Earth and the apple, I put Earth and the apple.
Isn't it only, so it's not only Earth that has gravitational force,
No.
it's everything? Like,
Everything. That's what we are just saying here. That the table and myself, we attract each other. That the sun and the earth attract each other. That all the galaxies, all the planets, all are connected by gravitational force. This is a problem that is a real experiment. How did they find out the value of the big G? So this is a very nice experiment, but you have to do it really precise. So this is a rod with two masses at the edges, okay? And this rod is being lifted, it hangs from this fiber. Okay? And on this fiber I have a mirror, a flat mirror like this. Forget about this A. This A is not in the problem yet. I have just the rod with the mirror. And I have this light, let's say it's laser. The laser touches my mirror, gets reflected, and points there on a scale. Okay, so that's the reflection of the laser into the scale. Now, this is a problem that is done in vacuum, not no friction, no resistance. Okay, so very precise experiment. Then I pick another object, this ball A, and bring it close to this ball here, not the other one, but close to this one here. What is going to happen? If it's true that there is this gravitational force, in this case it's force between these two boxes, not these two balls, what is going to happen? Oh, they attract each other. Okay, so I'm holding this one here. What happens? This one comes closer, a little bit, because of this force. What happens to the mirror? Oh, it tilts a little bit, and the reflection of the laser is not going to be at the same point, a little bit outside. And from that you can compute what is the big G. Did you get?
You can determine what's what?
The big G.
Oh.
Okay? Because I come to this equation. I know what is the masses of my two objects. I know the distance between them, so I can get the big G.
Why would the masses matter?
Because the
Here,
value
no,
of the
here.
force. The gravitational force, the force between these two objects, always depends on the masses. So it depends on this mass and on this mass, how much they attract. No? Think about it, I'll come
I'll have
back.
to think about it, yeah.
so, before we were looking at gravity, for example, when something was obviously already had a perpendicular Fn, is there something that's constantly going against gravity? Like if gravity's in one direction, is there something that's always working against
No,
gravity?
what could go against it? We could have some resistance, some air resistance, but out in space, there is nothing against the force that is pulling the moon towards Earth, or the force that is pulling Earth towards the sun.
So, in this problem, we move towards each other, so why aren't the planets moving towards each other?
Why? Why the planets are not? Why Earth is not falling
Because
into
of
their
the
orbit?
orbiting?
Huh? Why Earth does not fall on the sun?
High velocity.
We have the tangential velocity. So then we keep moving in orbit forever.
Some may say that, like, with the moon around Earth, that technically the moon is falling towards Earth, but because it's exactly the right amount.
That's the word that we use to say it's falling. It's constantly falling, meaning it constantly has this acceleration. But as a way of saying, it doesn't really physically move and collapse into the center of Earth. It just keeps rotating. It is the orbit.
Do we know where the tangential velocity came from, or is that Big Bang Theory stuff?
It's then is the whole story of how were the solar system created, how were the galaxies created. And so people have their theories. And the ones that remain in orbit are the ones that had the right speed. The ones that didn't have collapsed or escaped.
Flew off tangentially.
Okay, this problem here is to find the little g. Let me just finish this one and then we'll be done. How do I find the little g? I put the big G. This is on Earth, this problem. The mass of Earth and the distance. Which distance? In this problem here, what we have is the following. Here is Earth, and this is the radius of Earth. They give us there 6,380 kilometers. And on top of that, we climb the Everest, and we are here. So the Everest has more 8.9 kilometers. And we want to know what is the G that someone on top of the Everest would feel. Okay, so what is the G here? So I come to this equation. I'll put the big G that you saw is 10 to minus 11, that tiny number here. Okay, so I put the big G. I put the mass of Earth. Here is the mass of Earth. And in R, what am I going to put there? Not just the radius of Earth. If I just put the radius of Earth, I get 9.8. Now I'm going to put the radius of Earth, which is 6,380, plus the height of the Everest. Now all this I should put in meters, because if I'm using the big G in the units, you see here the units is meter and Newton, so I will put meters. So 10 to 3, all this. So if you put all these numbers, you will see that on top of the Everest, the little g already decreased. Instead of 9.8 is now 9.77 meters. A little bit different. If you keep going higher, it's going to get smaller. All right. So that's it. I think we talked too much. Next class we are going to solve the problem with the satellite.